All right, so in this video, we're going to talk about independence of path. And so the value of a line integral, which is what we've been working with in the last couple sections, now of a conservative, a very special type of vector field, is independent of path. And so in this figure over here, the arrows will denote the vector field. And in this particular case, the vector field is conservative, and we'll talk about what that means here in a little bit. But what this independent of path means is that if we are a particle traveling from 0, 0 to 1, 1, and we know that a line integral in context could provide us with the amount of work required. So the amount of work required for that particle to travel from 0, 0 to 1, 1 in this conservative vector field is not dependent upon the path it takes. So the amount of work from here up to here, same way along this curve and same way along this curve, will all come out to the same answer. And that's again because the vector field is conservative. Now, what does it mean to be conservative? Well, F is conservative if the vector field F equals the gradient of this lowercase f. That lowercase f is going to be called the potential function. And we'll talk about what that is and how we find that here in a little bit. But that's what it means to be conservative, if f equals the gradient of the potential function. Now, to figure out if the vector field is conservative or not, we have a conservative field test. So we'll go ahead and say that f, which is equaling PQ in this case, is conservative if and only if IFF partial P partial Y is equal to partial Q partial X. So it's a pretty quick determination to decide if the vector field is in fact conservative. And if it is conservative, then to compute the line integral, we can actually use the fundamental theorem for line integrals. And so that would be something like this, where we have an x0, y0 point on the bottom, and we'll do maybe an x1, y1 on top, our traditional f dot dr. This is now going to equal the x0, y0, x1, y1. And since f right here, being conservative, is now equal to the gradient of f, we're just going to substitute the gradient of the potential in there, dot dr. And since that's true, we can simply evaluate the potential function from x1, y1 minus f of x0, y0. So to compute the line integral, which could potentially be a more complicated process as we saw in the previous sections, by showing it's conservative, we can simply rely upon that potential function and evaluate directly at the 2 points. But a large part of this is obviously going to be discussing the potential function. So I'll go ahead and I'll clear the screen and we'll take a look at how to do this. All right, so to find this potential function f, we'll take a look at the example where our vector field f is equal to this right here. Now, the first things first, we need to, in fact, show that this is conservative. Otherwise, the potential function is meaningless. So to show it's conservative, I'll come over here to the side, and I'm trying to show that partial p partial y is equal to partial q partial x. And so remember, that was p and that's q. So if I take the derivative of p with respect to y, that's going to give me a 6y. And then I want to confirm that that's equal to q, partial q, with respect to x. And if I take the derivative of this with respect to x, I also get that 6y. So we are, in fact, conservative. Now, since we're conservative, we know that f equals the gradient of f, which equals partial f partial x and partial f partial y. And that was straight from the previous screen. So this also now means this guy right here is partial f partial x. Remember, f is now going to be equal to the gradient, which therefore has the 2 components, these guys right here. Therefore, the first component would have to be partial f partial x. The second component would be partial f partial y. So I'm just going to take this one. It doesn't matter which one you start with. I'm just going to take that one and say partial f partial x has to equal 3y squared. Now, I'm going to go ahead and integrate this thing And remember from Calc 1, it's essentially us moving this guy over here. And so I'm going to be integrating with respect to x. And on the left-hand side, the integral and the derivative will do away with each other, leaving us with just now f of xy. And so as I integrate this with respect to x, that's going to be a 3xy squared. And then plus our constant. But I can't just put a plus c there because I integrated with respect to x. That could have been a constant with respect to y. So I'm going to need to write that as plus c of y. And as always, you can work backwards to convince yourself that this is correct. If I take the derivative of this with respect to x, I need to come up with 3y squared. And again, noting that if this was a function of y being treated as a constant, it would still be the same. Okay, so we've got this so far. Now, what I'm going to do is I'm actually going to use this right here, and it's very important to understand this. I'm going to use this guy right here to find partial f partial y. Okay, so I'm using this to come up with partial f partial y. So when I do that, that's going to give me 6xy plus c prime y. Now, the reason why it was so important to use this to come up with it is now because I'm going to take it and set it equal to what we defined as partial f partial y from above. So I'm going to take this whole thing and set it equal now to what it was from the vector field. So that's going to be equal 6xy. I've got now an equation here to solve. This guy right here equals this, allowing me to solve for c prime of y. In this case, c prime of y equals 0. To get rid of that derivative, remember I'm trying to find what this is, so to get rid of that derivative, we'll go ahead and integrate, which means that c of y now just equals some regular constant c. So my final answer here for my potential function, f of xy, would equal 3xy squared plus c. And the nice thing about this is you can always take this potential function, because the gradient of it is equal to the actual vector field itself. Take the derivative with respect to x, and you should get this. Take the derivative with respect to y, and you should get this. So you can always check your final answer.